Hello, Physics Nation. My name is Nate Larmond, and I'd like to do a simple kinematics equation. We let a ball roll down a ramp, and we just did distance over time to find the average velocity. But then we did distance over time after it left the ramp. So we found the final velocity. Here is the final velocity in this other mathematical model. So what this guy is saying is if the acceleration is constant, the average velocity is right in between the initial and the final, or the final velocity is double the average velocity. And so that's the point of this experiment. Is this mathematical model true? Can it actually, predict an experimental outcome? So, like I said, it's just distance over time twice, but you can sort of see some patterns. And, well, we like to measure uncertainty and try to find sources of uncertainty. That's our favorite, experimental hobby. Pardon my scrolling. Let's start with the handwritten sample calculation. Here's our free body diagram. We had gravity, normal, and friction. You're not supposed to include motion in a free body diagram, but friction always opposes motion. So if the motion is positive x, negative y, the friction is negative x, positive y. And here, the velocity is all horizontal, so friction is all horizontal. Anyway, here are my little fill-in-the-blank calculations, just for raw pieces of data. How long is the ball on the ramp? How far does it move? So the ramp was 1.63 meters long, and then the floor distance was 1 meter. So, when the ramp stops, the floor begins. Friday night ends when Saturday morning begins. So when this timer stopped, this timer began. And here are the duplicate measurements, and distance over time provided 0.5 meter per second. Kind of crazy. So 1.6 divided by 3.2 is exactly 0.5 meter per second. And then we let the ball roll 1 meter beyond the end of the ramp, and another, physics miracle, 1 meter divided by 1 second is 1 meter per second. So we had a really clean 2-to-1 ratio, at least in first block. First block was more interested in, the consistency, the reliability, the precision of these different motions. Fourth block wanted to allow a bowling ball and a different ball. They wanted to do a shot put. I didn't have a shot put, but I did have a basketball. So they were more interested in mass and distribution of mass affects the motion of the ball. So here are the results from first block. Like I said, they were more about consistency. When the ball was on the ramp, we were really consistent because, well, I think it's because I provided a countdown. I gave 3, 2, 1, bam. Everybody started simultaneously, or had a good chance of starting simultaneously, and then stopped when the ball left the ramp. The floor times, however, I couldn't predict. It was when the ball crashed off the ramp onto the floor. So internet was kind of laggy, the Wi-Fi glitching out. It was hard. They were listening for that impact, but like I said, it was hard to be precise, and you can actually see the imprecision or inconsistency in the graphical display of data here, and it shows up in the data table. So for the floor, our standard deviation was 24 hundredths of a second, basically a quarter of a second. So we were bouncing around a lot, not very consistent at all. But on the ramp, we only bounced around randomly by 6 hundredths of a second. Very precise, very consistent, or reliable. Here is sort of take 2. Like I said, these guys were more interested in changing the mass, sort of changing the physical system. And we let a bowling ball and a basketball go. Interestingly, the basketball was much slower. So we're going to, get deep into rotational mechanics, but the ratios weren't as good. For some reason, we were not close to that 2-to-1 ratio. So 0.94 compared to 0.54, not very close to 2. This was better, 0.79 compared to 0.38. That is close to a 2-to-1 ratio, the final